Welcome back to ECE 441A, 541A. Exam number 3 is the next time we meet on Friday, but before that you have homework number 7 that's due, and if you want some extra material on sketching or designing controllers, there's another lecture. It's lecture 7.3. The lecture notes, I think, now are accurate. The video is there, and that's on PI control, which is sort of the stepping stone between phase lead, or one way of thinking about it. Phase lead gives you the zero closer to the origin. PI is like a phase lag, and that gives you your pole right at the origin, and your zero is now to the left of that pole. And then you have PID, which combines essentially lead and lag characteristics to give you maybe the best of both worlds. Lab number 3 is playing with phase lead and PID controllers, and you'll need to know how to design those. You won't necessarily have to execute lab number 3 or perform lab number 3, but you'll want to be comfortable applying phase lead and PID controllers to a particular system. Today I want to just repeat the process for our exams, and in particular exam number 3. It's changed a little bit. You can now bring in a little bit more hardware and one more sheet of notes, essentially. And then we'll talk about stabilizing unstable systems. The process for exam number 3 is 3 sheets of notes. We just keep growing. You may not need that many, but you can have one additional sheet, which is this photocopy of table 2.3, the Laplace transform pairs, and you need to bring that yourself. Unless you incorporate it into your 3 pages, that's fine also. The hardware that's additional now, you can bring a protractor if you want, and a ruler and dividers. Be careful if you are bringing dividers, but maybe you can get by with just a ruler. But if you need that, if you want that in your sketching and analysis with root loci, that's allowed. Just realize you have a fairly limited platform with which to perform your exam, so you'll want to maybe make sure that all your implements are conveniently available to you if you are using protractors and rulers and calculators. You won't have then access to a book or your notes, computer or cell phone. That way you don't have as much on your desktop, hopefully. There's no MATLAB usage on the exam. Unless you have it stored mentally in your head, you can use MATLAB knowledge, but you can't use the platform unless that platform is embedded in your processor inside your head, which is fine. Today what I want to do is talk about stabilizing unstable systems, and you're tired of hearing this, but when can you not cancel poles and zeros? You can't cancel poles and zeros in the right half plane, but that does not preclude you from putting poles and zeros in the right half plane, and we may have to do that today to stabilize unstable systems. I'm going to give you a few questions today, and the first one is, in this, and we'll be dealing with this traditional block diagram configuration: unity, negative output feedback, the plant G of S, and the controller G sub C. Now we have a plant that has 2 poles and a 0. Is it possible to stabilize that plant, or that G of S, with a controller that's restricted to being only a gain controller? And now what I would expect you to be doing is, on a napkin or on a piece of paper, on the back of an envelope, or if somebody gave this to you during an interview and they said, tell me about this system, can you stabilize it with gain feedback, pure gain feedback, then I would expect you, it's easier to not be thinking mentally in this picture, just sketch it. allows you to think more openly if you have things on a piece of paper or on a napkin. You can now sort of not have to remember everything all together. You can have it there mentally, a physical image in front of you, and now you can think relative to that image. And what would you put on this S-plane plot? Poles and zeros. And now where are those poles and zeros located? 1, 0, and -2. Now we just have to remember which one's which, but we have a pole at the origin, we have a pole at -2, and we have a 0 at +1. Now we have our poles and zeros sketched or located. What pieces of the real line segment belong to the root locus? And I'm assuming you heard that as well as I did if you're listening to the microphone. Maybe not. That was kind of joking. But we know this piece is on the root locus. What about the piece between s equals 0 and s equals -2? No. The piece between -2 and minus infinity? Yes. So now we have these sections or segments of the real line that belong to the root locus. Is it possible to stabilize this system with a pure gain controller? No, because now for k positive, that pole that starts on the imaginary axis stays in the right half plane for all values of positive gain k. And we can't stabilize this system with a simple gain controller. All right, that leads us to question 2. Is it possible to stabilize that system with a little bit more involved controller? And now let's just add in 1, 0, and 1 pole in addition to our gain. Now we have 3 parameters to adjust instead of 1. Again, we can locate our poles and zeros. Pardon? So now, is this a case for the phase lead or phase lag? Now when you know this system is unstable if you just used a gain controller. Now you want to be a little bit more broadly thinking or more creative thinking in terms of where do I put my poles and zeros. You may not want to be stuck in thinking, oh, it has to be a phase lead, oh, it has to be a phase lag. Just open up your thinking process and say, I just need to be able to stabilize this system. And in this case, what are we going to do? Or what's the thought process that you could possibly be playing with in trying to come up with a controller that stabilizes this? What's restricting this system right now if you just had a pure gain controller? That 0 in the right half plane, which is forcing that segment between the origin and +1 to be present. It'd be nice if we could somehow get rid of that, or at least change it so that for some range of gain k, we can stabilize this system. And now so the thought process 1 is we need to eliminate the root locus branch between s equals 0 and s equals +1. And now, how do we do that? Can we put a pole at s equals +1? What did I just tell you at the beginning of class? That's not allowed, is it? So if you were a little bit late, maybe you forgot, but I've been saying that many, many times. So that means But we can't cancel that unstable 0, can we? Or that 0 in the right half plane. Pardon? Put a 0 where? So now we have +1, we have -1, and -2. I hear somebody bidding to put a 0 at 1. Which one? Haha. -1 or +1? And it really doesn't matter where you put it in the right half plane. A convenient place might be right on top of an existing one, especially in this class, because that might eliminate your calculation of zeros, or I'm sorry, angles, or any other lengths that you might have to generate. Now you have two at the same point instead of two unique locations. But really, if we simply place a 0 in the right half plane, that's going to help us change our root locus segments. So this is actually going to change the root locus segments on the real axis. And so if you can experiment, you can play. You've got plenty of napkins or plenty of sheets of paper that you can play with, and now you have a virtual sheet of paper with all these phones and tablets. You can just scratch as much as you want. But if you, let's just do it here for starters, and I'm putting it offset just so you know there's two there, but they're right at the same place. Now what's the root locus look like? Do I have a segment between the origin and +1? No, because I don't. The phase angle at any point between 0 and +1 is not -180 degrees. I don't have an odd number of poles and zeros to the right of that any point on that segment. So that now has made that segment disappear magically, hasn't it? Which segments do I have any real axis segments on the root locus? Now I do have this piece, don't I? How many? Well, I can't just put a 0 down. I have to put a pole down, don't I? So where am I going to put my pole? And now we're not worrying about anything other than stabilizing the system. You could put it at -2. I might want to put it over here a little bit further because I sort of like what I have between 0 and -2. I could quickly sketch that, but which piece now of the real line belongs on the root locus? If I have this over there somewhere, I've now located this at, let's say, -P sub c. Which segments, did that change my root locus between 0 and -2? Do I have a segment between -2 and -P sub c? Do I have anything from -P sub c to -infinity? How many closed loop poles do I have? How many X's are there? How many open loop poles do I have? I have 3, so I should have 3 closed loop poles. I have 3 branches of the root locus. I only see 2 pieces. You said I have 3. Is it clear to you that some of these real line segments might possess more than one branch? And that's where you might now have interesting behavior. What's interesting about the root locus between 0 and -2? What's happening there relative to a rule? How many branches do you have of the root locus between 0 and -2? 2. And they can't just meet and stay. They don't like to just cuddle. Okay? They break away. So as soon as they reach each other, if you crank the gain up a little bit more, then they start moving away. We have two branches. One is here, and one is there. If that pole wasn't at minus P sub C, they would have split probably, well, no, it's a geometric mean between them relative to where the zero is located. But let's just, what happens now when they meet? They break away, and where are they going to go? They're going to the left or to the right? We need a traffic cop in here to direct traffic. Is that right or wrong or left, or which one is it? So the branches go where? They go towards zeros, and these zeros could be finite zeros or infinite zeros. Do you have any zeros at infinity in this diagram? What's your pole zero excess? 1. You have how many asymptotes? 1. What's the angle of that asymptote? 180. So you are now having one asymptote. You have a 0 at infinity, and it's at minus infinity. That's one of your branches. The other two branches end up on those two finite zeros. So whatever happens after you break away, these guys are going to the party at +1. For an infinite gain k, they will be in the right half plane, which means what? Can you stabilize this system with this pole zero pattern that we've produced? And now there's two questions. You might want to bring a coin to class, but really I don't want you flipping it during the exam on Friday. You can do that mentally, okay? You can flip that coin mentally. Heads. So is it stable? You have to select the right gain, don't you? And on an exam, what's the right gain? Is there one right gain? No. There's a lot of right gains. Is k equal, well, I don't know what k equals, but where could I determine the upper bound for, is there a lower bound or an upper bound on the stability of k? Upper bound, isn't there? At k equals 0, where am I? I'm at 0, minus 2, and minus p sub c. As I crank up the gain k, am I stable? If I crank up the gain a little bit, this guy's there, this one's there, and this one's there. Are those three in the left half plane? So I am stable. I crank it up a little bit more, the gain, and now I have to change symbols. Let's say I'm now squares. Uh-oh, I'm going to be figure challenged in a little bit. Symbol challenged. But do you see now how they are moving? Or am I still stable for that choice of gain k? Could you compute that gain k? Or on an exam, would you have to determine the breakaway to find a stable controller? On an exam, what could you do quickly to try to find a stable controller? Right now we have G sub c as k, s minus 1, s plus, let's just say 4. So this is now minus 4. It's not drawn to scale, is it? Oh, well. But what's k? Can you find a k quickly? Do you have to find the breakaway to find k? So here you don't have to overthink it too much. What you have to do is realize that for small enough gain k, where are you going to live on the root locus? The red path tells you all the potential closed loop pole locations. And to get to any of those, you have to fix the gain k. We want to fix the gain k such that we have a stable system. If I picked a k to get me to one of these triangles, I would have a stable system. My thinking would be, you know what, let me just pick s equal to minus 1/2. I know if I'm on that segment between 0 and minus 2, the other one's going to be somewhere on that segment also, and the third pole will be to the left of minus 4. Is that clear? So here I would say, oh, let me use the magnitude condition. I now have my controller pole at s plus 4. I have a pole at the origin. I have a pole at s plus 2. I have a 0 at s minus 1, and just to show you that I have 2 there, I have another 0 at s minus 1. And now I would simply evaluate that at minus 1/2. And I didn't have to find the breakaway. I just know that it exists. Now, if my breakaway is closer to the origin than minus 1/2, what's one of those poles going to be? If one is at minus 1/2 and the breakaway, is it clear what I'm asking? I hope I didn't mess everything up, but you didn't know that anything is below there, so you still have a blank page, correct? I haven't messed you. You haven't been swearing at me yet. Well, probably, but anyway, let's not go there. Plus 1, minus 1, minus 2, and then we had something at minus 4. What I was saying is, suppose do I have the right poles and zeros? Suppose that we've located a triangle at minus 1/2, but for whatever reason, the breakaway is closer to the origin than minus 1/2. Where's your other, you know you have another pole over here, but where's your third pole? Where's your third pole in this schematic or in this root locus? If I've picked the gain to be at minus 1/2, and for whatever reason, I don't think it would be this way. I think the breakaway would actually be a little to the left of minus 1/2. But just to think about, what if the breakaway was to the right of minus 1/2? Where would the third pole be located? What happens at the breakaway point? What kind of gain is that? Or what's K? It's a relative max, isn't it? So now you're cranking up the gain K from 0, and you're trying to get to a relative max here, and you haven't quite made it there with this triangle at minus 1/2. So where's the other triangle going to be? It's going to be between 0 and the breakaway. So worst case scenario, you actually have a slower pole than s equal minus 1/2. But where is that pole relative to left half plane and right half plane? It's still stable, isn't it? So it wasn't damaging your process of trying to stabilize the system. You just would need to pick a location between 0 and minus 2, go for it, and calculate K, and you've got a stable system. You didn't have to find the breakaway. You didn't really have to do too much other than throw that 0 in the right half plane, place a pole somewhere to the left, and then compute K. Is that clear? That maybe would have taken you 3 minutes if you knew the strategy to do all of those computations. Because you have 10 problems, okay, now you have 47 minutes to work the rest of the 9. Questions on this? Any questions? Let's do another question. Yes? So a pole at the origin is marginally stable, but you really don't want to be operating on the imaginary axis, and with a little bit of a gain k, you've now pulled that into the left half plane. We want to live on the root locus. We have to live on the root locus. We just want to pick a gain k to get us into a stable place. Here's question 3. Can g of s equal to 5s over s minus 2s plus 2 be stabilized with a pure gain controller? What's your first step? Is that right? I had a 0 at the origin, I have a pole at minus 2, and I have a pole at plus 2. Is this system stable for a pure gain controller? What do you have to do? Now you just have to go to step 2. Step 1 was to put the poles and zeros down. Step 2 is to place the root locus on the real line. Which root locus segments, or which real line segments, belong to the root locus? This poor guy is stuck, isn't he? Between 2 and the origin, for any gain k, positive gain, it's unstable. So you can't stabilize this. The answer here, if you were flipping a coin, was no, and the answer is what? We don't even want to have an infinite gain here because you're still really unstable. You're always in the right half plane. And you could say, well, I can never have a pole leave the right half plane because of the root locus diagram. It verifies that I'm always unstable. So you know my next question. Find a controller that will stabilize that system when the controller is something other than just a pure gain. Did I make this announcement? Special office hours tomorrow from noon to 2. I'm busy tomorrow, but I'm going to squeeze those in. That's fine. Here's question 4. Moving on. What do we have? What do we want to do now to try to stabilize this system? We need to again change that segment between the origin and plus 2, don't we? How do we do that? Can we put a 0 on that pole at plus 2? No, 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 right? We can't cancel anything in the right half plane. Do we want to put a 0 in the right half plane in this case? Probably not. So what's our next option? Can we throw a pole over there? What happens if we put a pole over there? And now just Put one down. Don't try to think too much. Just throw one down. Put one there. And say, what happens now? And what else do I need? I need to put a 0 down. Well, I don't really. You don't always have to have a 0 to balance your pole. You do have to have a pole to balance your 0. So I could just put in a pole and change my pole 0 excess. I probably don't want to do that because now where are my asymptotes? Plus and minus 90. And so they're going to go off to infinity. Why don't I just do this? Why don't I put a 0 right there? Now what does my root locus look like? Which real axis segments belong to the root locus? How many pieces of bread do I have? And now you might have maybe a couple of right answers if you effectively somehow have been able to slice that bread and patch it back together at -2 by that pole 0 cancellation. So you really have 4 segments. One at 4 to plus infinity, between 2 and 4, between 2 and 0, and from 0 to minus infinity. 4 pieces. You can really sort of virtually erase that pole 0 cancellation, cover it up if that's messing you up in terms of thinking about how to sketch the root locus. It's virtually gone. So what segments now belong to the root locus? And now this is a homework problem, I think. What's the root locus look like? What happens between 2 and 4? A breakaway. And where do they go? How many zeros, how many finite zeros do you have? 1, effectively, because the other finite 0 was canceled by the pole. How many infinite zeros do you have? 1. And where's that infinite 0 when you have 1? Minus infinity. So these are what? Going to break away, and once you have that, now you know you have this circle. Those are supposed to meet up. They're supposed to re-enter at the same place. I'll just make that there. And now what do we have? Do we have an upper bound on the stability value for K, a lower bound? Do we have any Ks that we can stabilize the system with? We now have a lower bound, don't we? We have to crank up the gain enough to move us into the right half or into the left half plane. We have to crank up the gain to get us beyond those 2 imaginary axis crossings. On an exam, if you had to quickly put together a stabilizing controller, you wouldn't even have to find those j omega axis crossing points, would you? Would you have to find the breakaway? You don't even have to find the reentry. Do you? You know the reentry is now somewhere with a radius between, let's say, 2 and 4 for a radius, so you now know the reentry is going to be somewhere between -2 and -4 in the left half plane, and you really don't even need to know. I would do the following. I would say, let me crank up the gain to get me to maybe that location, enough to be on the real line. And once one's on the real line, you know the second one's on the real line. And whether or not you're on the left or the right of that reentry doesn't really matter. Your other one's going to be on the real line. Is that clear? So you didn't have to find the breakaway. You didn't have to find the j omega axis crossing. You didn't have to find the reentry. You just have to know the picture and then say, oh, unless I ask you for the minimum value of gain K to stabilize the system, then what would you have to find? You could do it many ways, but here you might find the J omega axis crossing, maybe with the Ruth array. Once you found that omega, you could use that omega in your K formula to find the gain K that's the smallest K to stabilize the system. And that K would obviously depend on where you located that pole at +4 or whether you put it on top of the pole at +2. It really depends on where you locate that pole. Do you see all the different options? Let's say that we now had the same system, whatever that system was. That's what we started with. Maybe a simple controller would be, oh, can't put that guy right on top of that and cancel this one, so that now I have G sub C is now this K S plus 2 over S minus 2. And my G was 5S over S minus 2, S plus 2. And what might I do? I might say, let me just locate a closed loop pole at -1. For this picture, what do you actually know is going to happen? What's the radius of your radius is 2 now for your circle. And you now know, if I had sketched this properly, that you're now doing this. Oh my. Those are supposed to be coming in at -2. One's going there and the other one's going there. You can hopefully draw better potatoes than that on the exam. That's why I said, well, I didn't say you could bring a compass, but you can if you want. You don't have to get that detailed on the exam. A potato that shape is fine on the exam. So now how do I find the rest of the controller? What's left to be found? K. And if I picked a closed loop pole at -1, I now can say, okay, I'm now letting S delta equal -1, so that I can now, from the gain or the magnitude condition, I have K, S plus 2, S minus 2. That was my controller. My plant was S minus 2, S plus 2. I don't need to worry about those two factors because they canceled, and that's equal to 1. I can now solve for K. I now know that K is equal to S minus 2. I have 2 of those. I have a 5 that I can't forget. And I have an S. Is that okay? And I said I wanted to place those closed loop poles when S was equal to S delta of -1. Now I have 3 upstairs. As far as length, I have 5, and I have from the origin to -1, that's a distance of 1. There's my gain. And now I have a stabilizing controller for that original question. Fairly quickly. I just had to know the structure of the root locus. I didn't have to know the J omega axis crossing. I didn't have to know the breakaway. I didn't have to know the reentry. I just needed to realize, oh, at some point, at some value of gain K. And that gain's not too big, is it? It's less than 2, and it's already zipped me around that circle and put me on the real line. And now all the way from 2 to infinity pushes me to the origin for that one pole. Questions on that? All right. See, we've gotten through 4 questions and we still have 10 minutes left. So just take this like Friday. Now we need to speed up. Now what can we do? Let me ask you another one. Can one stabilize g of s equal to 4 s minus 1 s plus 2? This is question 5 if you're keeping score. Question 5, this is now k with k greater than 0. So what's the first step? Put the poles and zeros down. And where are my poles? Is that what I have? This is my S-plane. Is it possible to stabilize this system with a pure gain controller? Yes. I'm almost ready to break out in some cheers here. That was a pretty resounding yes. Why did you come to that conclusion so dramatically or so confidently? Because you know the root locus. The root locus is easy. This used to be a cheer. It'd come together and go apart, right? That's what it is. You're now coming together and going up, and your asymptotes are at plus and minus 90. Where's the breakaway? It's halfway between plus 1 and minus 2, isn't it? And their separation is 3, so halfway between that is 1.5 between those two poles. Or it's now at 1/2. So that we now are coming here. Can you find the lower bound on K for this system to be stable? Is that a challenging question? Not if you can see the root locus. You need to crank up the gain K enough to push you into the left half plane on this root locus. And where is that going to happen? I'm getting tired of symbols. I'm going to draw a cloud. So, oh, a star? Really? All right. I'm taking requests from the audience, apparently. So now if we have a star there, where's the other star? In this particular case, it's going to be 1 away from where we started, just like the other one was, right? And now what's the magnitude condition is going to be true, and we had K, and we have now, what, S minus 1 and S plus 2. Did we have a gain anywhere in the numerator? No. And that's going to be 1. So that now we have K is equal to S minus 1, S plus 2, and a lower bound for stability. What? I asked if there was a gain in my G of S, and I didn't hear an answer. How's that? Pardon? Does that look a little bit better? And now we have to be at star. And what was star? Star was actually a 0, wasn't it? So now if we plug in 0, 0 to plus 1 is 1. 0 to 2 is 2. Divide by 4. So K equal to 1/2 is our lower bound for stability. If we crank up the gain beyond 1/2, we will have a stable system. Do you know the gain K at breakaway to get you to the breakaway point? You can calculate it now. I could use a cloud, couldn't I? It's going to be K, the same formula, evaluated at S equal minus 1/2. And that will give you the K value at the breakaway point, which is obviously going to yield a stable system. Questions on that? So for stability, we would want K bigger than 1/2. Did you ever in your homework, hopefully you've started your homework, it's due tonight at midnight. If you haven't started your homework, maybe you might pay attention to the following condition. Did you ever find the angle when you were trying to calculate the angle of your pole to locate your controller's pole location using the phase angle condition? Did you ever get a negative angle for theta sub p sub c? What if theta sub p sub c is negative? During a controller design? Do you just drop back and punt and go into the locker room? You can cry. After a good cry, what happens? So now let me just put something here so that you can see what I'm trying to cook up. Suppose that you had a system that looked like that, and you wanted to end up going, so let's say this is now at minus 2, and you wanted to go through plus and minus, or minus 2 plus and minus J2 with your closed loop poles. And let's say that you hadn't been paying attention in class, and so you really don't know how to design a controller, and you put down a 0 right there at minus 4. And you're now trying to find a pole location to get you, or to have your root locus pass through that triangle. So you have this angle, you have this angle, you have the angle of your controller, and you have this that you're trying to find. The system is now G, was 1 over S, S plus 2. The G sub C that you're trying is K, and you said, oh, let me put this at 4, and now I'm trying to solve for P sub C. From the phase angle condition, pardon? How did I set up the triangle? From the design specs. So the triangle is coming to you from the design specifications, or on an exam, it might just be handed to you. Or if you now need to stabilize a system, you may have the choice of picking that triangle. But design specs like percent overshoot, settling time, peak time, those might then suggest a triangle location. In this case, I'm just saying assume that's where we want our closed loop poles. Now that we have that, we want to do the phase angle condition, and the phase angle condition says we have our zeros angles minus our pole angles. Those have to equal minus 180 degrees to give us a stable system. And I've cooked this up to give us easy computation of angles. What's the angle from the origin to minus 2 plus J2? 135. It's 90 from the second pole, and it's 45 from the 0. So that I now can say, oh, I have 45 degrees minus 135 plus 90 plus theta p sub c is equal to minus 180. If I solve this for theta p sub c, I now have 180 plus 45 minus 135 minus 90, 0 degrees. Ugh, what does that mean? That means that I don't have a solution for this choice of S delta and that 0 location of my controller. That combination is causing me to not have a realizable controller. So I either have to change my triangle or my 0 location or both. In this case, what's the obvious choice? Just slide that 0 over. Do you see if you slide that 0 over, its angle is going to get bigger, and now theta sub p sub c's angle will become positive. Now I can solve it. And the trivial way is to slide that 0 right on top of the pole, and now you have the cheer, right? Together and apart. So now Friday, everybody's going to come in cheering, right? We'll see you Friday, ready to go. Good luck.